Here's 11.1 goodness of fit test. So the warm-up was to read 11.1. Hopefully you've done that. So what are we doing? It's an inferential procedure, which is using stuff from a sample to make a conclusion about a population, used to determine whether a frequency distribution follows a claimed distribution. So are the proportions what they say they are? So instead of one proportion, it'll be many proportions. So our expected count, or value, is n times p, where it's the sample size times the probability, or the frequency. Not the proportion, but the expected count. For every goodness of fit test, you use categorical data. It's categorical data, it's not quantitative anymore. We use Hantum, not Phantom. We don't have parameters. Our H0 is always the claimed distribution is correct. Our alternate is that one or more categories are not in the correct proportion. We may need to rephrase that first one, but that's what it is. It's always right-tailed, and now we're using the chi-squared distribution. Properties of chi-squared distribution. We look over here, it's kind of faded, but it's not symmetrical. It's skewed right. Very skewed right. Shape depends on degrees of freedom. All values are non-negative because it's chi-squared. They are squared, so they can't be negative. And area under the curve is equal to 1, just like it always was. So here is a low degrees of freedom, a little bit higher, it starts to get a little bit more symmetrical, but still skewed right. So here's our test. Calculate the expected counts. Then we write the hypotheses. That's our H. Assumptions and conditions. Needs to be random, the 10% rule, and all expected counts are at least 5. If they're not, we can't do it. Our test statistic is chi-squared, which is the sum of all the observed minus the expected values squared divided by expected. We run the test. So we find our p-value, conclusion, we make our conclusion. It's very similar to what we've been doing before. So, for example, we want to test a claim that a certain die is fair at alpha equals 0.05. We get the following data when it's rolled 120 times. We get 25 one time, 25 ones, 20 twos, 14 threes, and so on. Now the expected count is going to be, everything should be equal. N is 120, that's how many times we roll it. P is 1/6. The probability that we get each one of the numbers is 1/6. So 1/6 times 120 is 20, and that's how we got these numbers. Then we do observed minus expected squared divided by expected, and that is going to be our chi-squared contribution, because the sum of all of those is our chi-squared value, our test statistic. So this is our test statistic, the sum of all of those. So 25 minus 20 is 5. 5 squared is 25, divided by 20 is 1.25. Well, 20 minus 20 is 0, so it's 0. We have 3 of those. 14 minus 20 is 6. 6 squared is 36, divided by 20 is 1.8. 21 minus 20 is 1 squared. 1 divided by 20 is 0.05. So these are our chi-squared contributions. So if we were to reject 1.8, the number 3 would have been the one that is the one that caused us to to reject our hypothesis. But let's see. So we add those up, we get 3.1. That's our chi-squared value. So our hypothesis. All sides of the dice are equally likely to occur. So they're all equal in this case. They don't always have to be equal, but they're what they're claimed, and in a fair die, they are all equal. Our alternate is at least one side occurs differently than expected. It could be more, or it could be less. A, our assumptions. All expected counts are greater than 5. Yep, they're all 20. That's good. Random. Yep, it's random. We rolled the dice. And clearly 120 is less than 10% of all possible rolls of a die. Name, goodness of fit test. I know it sounds awkward, but that is the name of the test. Our test statistic is 3.1. We already went over that. So the probability of chi-squared being greater than 3.1, it's greater than because our tests are always greater than with chi-squared because they're always right-tailed. Now how do we get that? So under menu, statistics, distributions, chi-squared CDF. Lower bound was 3.1. Our upper bound is our infinity, and degrees of freedom is the number of categories minus 1. There's 6 categories, either a 1, 2, 3, 4, 5, or 6. So degrees of freedom is 5. We're going to have low degrees of freedom, and that's okay. And there's our p-value. We can do the same thing here. Second distribution. Probably should have gone from the other direction. Chi-squared CDF. So it's from 3.1, comma 9999, comma 5. And we get the same thing. So we have a big p-value. 0.6845. So that is not less than our alpha, so we fail to reject. So we have insufficient evidence to reject the null, ergo, it's the same as what we've been doing. We cannot support the claim that at least one side occurs differently than expected based on our sample at alpha equals 0.05. Or you could say we cannot support the claim that the die is unfair, because that's what this is saying in other words. So you have you can kind of say it in a couple different ways. But if we just say it as what our alternate says, it might be easier. So that's one example. Here's one we're going to use the calculator. So we're trying to test to see if NHL players are born equally throughout all the months. There's a claim that they are born early in the months, and you can read the whole question later. So you can either say that the proportion of January through March is equal to the proportion of April through June, equal to the proportion of July through September, equal to the proportion of October through December. These are birth dates. Or at least 2 of the proportions are not 1/4. Really, it should just be at least 1. Or we can write it, the proportion of hockey players' birth month is the same for each set of 3 months. The alternate, at least one group of months has a proportion different than the others. So, we have our hypothesis. Expected. Well, we expect it's uniform. So there's 4 categories, so the probability is 0.25, and there's 80 players, so 80 times 0.25, there should be 20 in each of these months. So we put 20. Now, the way we do this is we put these in lists. So if we're using the Inspire, we have, these are our observed counts, these are what the actual data is, and these are what we expect, 20 in each. So observed and expected, I labeled them. If we're using the 84, you just put them in your list. Same thing, are observed and then expected second. It's better to put it in that order. So all the expected counts are greater than 5 because they're all 20. Clearly 80 is less than 10% of all NHL players. It means there's over 800 players, and there is. And it is random. It says random somewhere in the problem. Name the test, goodness of fit test. Now let's actually just run our test. On the 84, second quit. Under stat, go over to tests. Chi-squared goodness of fit test. Our observed is in L1, our expected is in L2. Degrees of freedom is 3 because we had 4 categories. We split up the year into 4 groups of months. And then we calculate. There's our chi-squared value, our test statistic, our p-value, and our contributions. Our contributions tells us which ones made us fail. The higher the number, the more likely it made us fail. To get that, you go to list, and it's under number 7. Hit enter, you can see the first group was 7.2, second one was 0, third was 0.8, last was 3.2. So 7.2, the first 3 months, was the one that really caused us to reject and have a very low p-value. If we look here on this calculator, we can go to a new page, just a calculator page, menu, statistics, stat tests, goodness of fit, observed and expected, degrees of freedom 3. And here we want the comp list if we want to see which ones give us the most trouble. You hit var and you go to stat comp list. So we get the same number, 7.2, 0, 0.8, 3.2. So what that means is that this first group was the most different. 32 is the most different from 20. 20 is exactly 20. 16 is only 4 away from it. 12 is 8 away from it. But 32 is 12 away from it. So it's the first 3 months that caused it to reject. So we have a chi-squared value of 11.2, p-value of 0.0107, which is definitely less than 0.05. So we have sufficient evidence to reject the null. Ergo, we can support the claim that the birthdays of NHL players are not uniformly distributed throughout the year based on our sample at alpha equals 0.05. And again, there's many different ways you can say that, but I think that's a pretty succinct and efficient way of saying our conclusion.